Welcome to Engineering Innovations, the official podcast of Purdue University's Elmore Family School of Electrical and Computer Engineering. I'm your host, Kristin Malavenda, the Communications Director for Purdue ECE. And my guest today is Peter Bermel. He's the Elmore Professor of Electrical and Computer Engineering, and he's a leading researcher in microelectronics. Peter's at the forefront of developing innovative materials and designs that are revolutionizing the way electronic devices work. This research not only enhances the performance of technology we use every day, but it also aims to make it more energy efficient. So join us now as we delve into this groundbreaking research, explore the future of microelectronics, and discuss how advancements could shape our everyday lives. Peter, thanks so much for joining me today.
Yes, thank you. It's a pleasure to be here.
So let's start kind of back to how you became an engineer. How did you get on the path to being an engineer? And then once you were an engineer, how did you decide this area to focus on?
Yeah, that's a great question. I think the first real engineering that got me excited was the space shuttle. And that was so inspiring to see that humans had the ability to launch themselves to outer space and then come back safely. And after that, I realized that I needed to be in this space of science, technology, engineering, and math. But I didn't know exactly what the best path was. And so I actually started in biology briefly, and then I realized I really liked physics, and then I got physics degrees for undergrad, master's, and PhD.
Okay.
But then once I started postdoc, I realized that physics had so many important applications, specifically relating to electronics, that I realized I really wanted to go more towards electronics and photonics. So that's where I've been ever since.
Can you explain in basic terms to our listeners what your research is in microelectronics?
Sure. Yeah, I'm working on a number of different topics related to microelectronics. And so some of these topics are related to finding new types of materials for electronics. And so in those cases, we're actually trying to characterize new materials' properties, and especially like more exotic or unusual materials. And these can include what are called bulk materials, in which you have like uniform set of atoms throughout the mass. It includes also what they call like quantum confined materials, which are basically very thin in one or more dimensions. And so you could think of it as a single layer sheet, or sometimes like a nanotube that's very, very small. And then we also try to compare our experimental predictions to what people are seeing in experiments, and then in some cases help with some of the experimental measurements and interpretation. And then we also look at devices. So basically, once you have these exotic materials, what kind of new devices can you make, and what are the changes in performance that you can achieve? And so this kind of spans the range from microelectronics devices to optical or photonic devices to quantum devices. And so these are all kind of merging together as you get to small enough length scales, like which are on the order of nanometers. And just to give you a sense of how small a nanometer is, if you think of the thickness of a human hair, it's 100 microns. And so it's actually 100,000 times thinner than the size of a hair.
Yeah.
So it's very small.
Yeah, absolutely. When you talk about all these new materials, how do the different materials change the landscape of microelectronics, or what you're doing?
Yeah, the materials can change everything because they're so powerful. They're the foundation of everything we do today. So many of you have heard of silicon chips, and you know silicon is a very powerful material in its own right because it's been the platform upon which we're building so many chips today. However, what we've realized at the same time we've done so much on silicon is that we also need other materials besides silicon if we want to have the full range of capabilities. Because silicon is really good for things like logic and memory and chips, but it's not as good for things like high power applications. It's not as good for lasers and a few other things. I won't list all of them, but there are other things that other materials can help with. And especially like once you get to either very high power densities or quantum capabilities, then it's important to look at a very wide range of material options. So once you have these new materials, then you can combine the strengths and capabilities that silicon brings to the table and bring in all these new other capabilities. And so if you think of like what's happened with phones, that's probably a good place to just understand as a standard consumer, right? So you used to have these rotary phones, right, which basically are dumb phones. They basically can do almost nothing. And then you had like the cell phones, and then the cell phones, like flip phones, by comparison to the rotary phones, seemed like amazing. They're much more advanced. You can type in the numbers, you can send text messages, you can do all this other stuff. But now if you look at like the iPhone 16 and so on, right, like that's a huge leap in advancement. Like there are so many new sensors, new capabilities, like you have very high quality pictures. You have so many other capabilities that you would not have had if you were to stick with like the rotary phone approach, right? So bringing in chips is what's enabling all this stuff to happen. But the point is, even as advanced as iPhone 16 is, we're not even close to being done with what's possible. Like in the future, we could have quantum secure communication. We could have ultra low power AI. And then you could have like basically what's called AI on the edge assistant that can answer any of your questions like on your phone rather than having to go to centralized website. And it can also make real-time adjustments. It could also enable things like autonomous vehicles and many other capabilities that people are getting close to but aren't necessarily like fully deployed right now, right? So, and there's so many more things that I probably haven't even thought of.
So what is these things that we're close to, what's the barrier to getting to that next level?
Yeah, it always depends on the problem, right? Like every problem space is different. However, I would say a couple of things. Like for quantum technology, one of the key limiters in terms of quantum communications is the range. So in other words, if you send a quantum signal down fiber optics, then the signal gets attenuated as it travels. And so you need really like a quantum amplifier to actually like pick up the signal, which is very analogous to what we have today for classical information. So that's why internet is based on fiber optics. It can span the whole globe without a problem because the classical signal can be amplified very easily. But for the quantum signal to be amplified is a much harder technology problem. And so that's something that people are actively looking into. So for other things like autonomous driving, I'm not as deep on that topic, but I do understand that there are a lot of like edge cases or corner cases that are hard to deal with. And so that's actually one of the biggest challenges in AI, like to have fully accurate and reliable answers from a given AI. Like, so even if it's successful 95% of the time, for many applications, that's great and it's totally fine. But then for things like vehicles where it can be a life or death decision, you have to have a really, really high standard. And so that's probably the biggest challenge in my mind, at least.
Yeah, that makes sense. We talk about energy efficiency a little bit. What role does energy efficiency play in your work? Why is it important?
Well, energy efficiency is really important for AI especially. So I'll start with the AI example, right? So one thing about AI is it's becoming more and more powerful. You have companies like NVIDIA putting out more and more powerful multi-processor cores, which are called graphical processing units. And then in some cases, they're even more specialized hardware called neural processing units and tensor processing units, right? And all of these things are unified by a desire to have like large-scale distribution of tasks and then basically like run all those tasks and then kind of collate the results together and then like rerun the calculation. So it just is doing this big leap across like a huge amount of hardware. And so as we add more and more pipelines and we make these things bigger, they get more and more capable. But at the same time, they're chewing up more power. And the reason is as you get a bigger footprint, then you have to send information on copper across a longer distance. And if you remember basic electrical engineering, where you say V equals IR, then basically if you have a bigger distance, then the resistance is bigger. So it's well known resistance increases with distance for same material. So you just end up burning up more power, so I squared R. So it goes proportionally to the size, essentially. So if you want to solve that problem, you need information transmission paradigm that's lower power. And so actually the photonic structure has enormous potential to solve that issue. And the reason is that photonics can have much lower transmission losses. When you're transmitting like on fiber optics across the world, oftentimes the losses are on the order of like 1 dB per kilometer. So that means like you're just losing a few percent after transmitting a kilometer. So that's actually really good compared to transmitting on copper. And people have tried to transmit long distances on copper. There was the so-called DSL or digital subscriber line technology out a while ago, but the losses were too high and the bandwidth was not high enough, so it's not a very popular technology now. Although there is also like cable, and then cable actually uses radio frequency communication, and then you have fiber optic communication to bring high-speed internet to people's homes. That's being more and more widely deployed now, especially in the US and other advanced countries. So what the basic bottom line is how do you take the technology that works at long distances and bring it into like these small scale, like chip scale devices? And that's actually a very active area of research that I'm part of.
So interdisciplinary research is a big thing across all subjects. How does interdisciplinary play into your research, and what's the benefit?
Yeah, so multidisciplinary research is important for so many reasons, but ultimately the biggest reason it's important is usually like if you're within a discipline, then you're basically like kind of working on the edges. You're trying to like kind of push things forward a little further, like kind of push performance or reliability or some other metric based on the disciplinary tools that are available. But then if you're looking for major breakthroughs, oftentimes they happen at the boundaries between different disciplines, where people in field A and field B don't know critical insights from the other person's field, but then they're absolutely essential to actually solving the problems that they're stuck on. And so oftentimes it's like kind of broadening like the knowledge base in very strategic ways in order to like have breakthrough solutions to important technical challenges. So I think what's helpful to me about having the physics background is I feel like I'm interested in a wide range of topics, and I'm able to try to work across some of these disciplinary boundaries. Even though I am firmly rooted now in electrical and computer engineering, I have a lot of collaborators across different fields, including materials, mechanical, in even industrial engineering and engineering education and many other topics.
So in addition to your research, you're also the PI and co-director of the SCALE Microelectronics Workforce Development Program. Tell me about that program and what are its goals?
Yeah, so first of all, SCALE is a very exciting program, and it's intended to address the fundamental challenge we have in the United States. So United States created the semiconductor industry, as you know, and that's why electrical engineering is so successful here in the United States to this day, right? So that's really great. At the same time, though, as we advanced the technology, we ended up outshoring a lot of the manufacturing capabilities to other countries. And so that put us in a very complicated situation the last few years, especially during pandemic, because while obviously we had the technical knowledge at the fundamental level, especially in the R&D side, we also were not always like producing the chips that are needed for everyday life. And as you may or may not know, everything with an on-off switch has a chip in it. So therefore, everything nowadays pretty much has an on-off switch, like I was talking about with the phones. That applies to almost every technology, including things like refrigerators, for that matter, and vehicles, and many other things. So we have to be cognizant that chips are essentially the lifeblood of our economy and our standard of living. If we don't have chips, then we're basically going back like 100, 200 years, right? Yeah. So that's a big problem. We don't want to go back. So how do we keep moving forward? But then how do we also have the in-house capabilities to produce what we absolutely need, but then also work with other countries in a collaborative way to learn from each other. So we're not also like putting ourselves on an island and then stagnating in that way, right? Because it's international ecosystem. So, but the U.S. needs to have its own capabilities, as well as many other countries need their own capabilities in order to produce what's needed to keep the economy going, keep standard of living up, and everybody happy. So because of all these needs, we need more people in the United States now to ramp up our semiconductor manufacturing. And it's not just ramping up the U.S. capacity, but it's also the global capacity is ramping up. In fact, it's expected that the size of the semiconductor industry will roughly double in the next 5 or 6 years, from about 500 billion to 1 trillion per year. So it's getting to be a really, really big and very influential and important industry because it's just showing up in everything. And as a result, if U.S. doesn't take initiative to push things forward, then we're going to fall behind, right? And so the point of scale is essentially to get more students involved in the microelectronics semiconductor sector. And I think that has been much more successful than I would have even originally expected, because originally we started in 2020 with 25 students across several different universities, mostly in radiation hardened technologies. But now we've expanded to 1,000 students across more than 30 universities. And we're still growing. So that's the most exciting part to me. And so we're able to leverage the investments from government agencies in order to bring lots of faculty, lots of students, and lots of industry and government employers into the table to understand what do they need in order for the industry to be successful in detail. And then also make sure that the students actually have the opportunities to learn those things, and then also get jobs like both internships and full-time placements after they graduate, as well as have the opportunity to go to grad school and do other exciting opportunities. And of course, I think the social aspect of connecting with like-minded cohort of students is really important. So hopefully this will make semiconductors, microelectronics a little more exciting and socially valuable. I've always said my goal is to make this profession is like being a doctor, right? Right? Because being a doctor is absolutely vital to society, and it's very prestigious, it's very important, and it's remunerated well. And I think that electrical engineering and related fields need to fall into that same category for the broader society, because parents and families need to encourage their kids to look into this field if it's right for them. It doesn't mean every single person needs to go into it, but if they are inclined towards engineering, if they love solving math problems, if they love tinkering with toys, those are all people who might be candidates to go into these fields. So they need to consider that this is a really exciting and important career path. It's benefiting society, and it's also good for the individuals. So they should definitely consider that.
So you work with a lot of students in classes and on your research. What qualities do you look for in a student before you take them on maybe to go on your research? What makes a good engineer?
Yeah, that is a great question. And I would, in fact, counter to say there's not a one-size-fits-all answer, because it really depends on what problems you're trying to solve. And so what's great about engineering fundamentally is it's you're solving problems. So if you like to solve problems, I would say that's the most fundamental thing. If you don't want to solve problems, or if you want to create problems, maybe not. But assuming you want to solve problems, there are a whole bunch of different skill sets that you could have in engineering that you could use to play a role. So you don't have to be necessarily a math whiz to be an engineer. You don't necessarily need to be somebody who can do mental math in their head. You don't need to be somebody who conforms to some other stereotype, like wearing glasses. That doesn't matter, actually. What actually matters is you want to find problems that are really hard, but interesting, and have important technical content. And then you're willing to apply your skill set and develop your skill set to try to solve them. And I think that's what is really interesting about engineering that people don't always appreciate. They may think engineering, you're just building a railroad or something, so what's the big deal? Everybody's already done that. So, but actually nowadays, you're just trying to solve really challenging problems that nobody's solved before in most cases, both in industry, in government, and in academia, right? So whatever sector you would go into in engineering, there's going to be a lot of great opportunities.
And I'm sure in your research over the years you hit certain roadblocks and you have to think of a different way. How do you help your students understand that you're going to hit those roadblocks and how to get around them?
Yeah. So I think, first of all, there are so many possible roadblocks that you can run into, it's hard to know in advance which ones will actually get people stuck. So I think the point is, like, you have to just be very creative, I think, about thinking about what are ways around those problems. And you can't give up easily. Like, that's very important. You have to have some level of persistence, but you also have to temper that with some level of realism. Like, obviously, there are some problems that are very hard and probably impossible to solve, right? For example, if I said, I want to fly with my bare hands today, that's not going to happen. But that doesn't mean that we can't fly, right? Like, there are ways to fly, but it's just not using that specific method, right? Like, we need to be more broad and more creative rather than just like overly prescriptive and narrow in the way that we think. So I think if you can broaden your mind, broaden your horizons, that's actually a really good way to approach engineering. So you do want to know what the technology is, you want to know what the physics is, and you want to be based on the physics at all times. But you also don't want to constrain yourself so much that you're basically psyching yourself out of the solution or talking yourself away from the right path.
Right.
And oftentimes it's very hard to know what that path is, but you just need to keep exploring until you can find something.
Mentoring is a big part, I assume, of what you do. What do you feel like your responsibility is with your students to help them along the way?
Yes, so I think in honesty, like, my goal, especially with PhD students, is to help them help themselves so they can be like subject matter experts on their topics. And so I don't necessarily always teach my students everything they know, right? So I think that's really important to emphasize. So of course, at first, I would have to be very directive with many students and be like, okay, well, you need to look at this paper and read this paragraph and do this, do that, right? So I will start with that method, but my goal is to move to more of a coaching role where basically they have a general idea of like what they're trying to do, what they're trying to achieve. And then I'm trying to give them some suggestions, like, you know, you're trying to do this, but maybe you need to do it a different way. And here's like some resources you might want to look at to see if this is a better option, right? But not necessarily be overly prescriptive, like I was talking about earlier. If you're too direct and narrow-minded with especially research students, then oftentimes you could miss a lot of solutions. And almost even more importantly, actually, they would not necessarily develop the skill set to think independently if you don't nurture that in the students. And so I think it's really critical to equip them with the tools they need to understand the fundamentals, but also give them freedom to explore things.
So looking ahead to the next 10, 20 years in microelectronics, what do you see as what the goals are and what do you see happening?
Yeah, so obviously there are some industry roadmap goals. So essentially to move to more and more advanced nodes for manufacturing memory and logic. I also see like a much bigger role for quantum technologies coming up in the next 10 to 20 years. Quantum is going to become mainstream pretty soon. It's already available, in fact, commercially, which many people may not realize. So for example, IBM and D-Wave and several other companies do offer quantum computing services, and it's being used by researchers worldwide today. But there's a lot more to come. We may eventually have quantum built into things like your iPhone. And quantum sensors are very powerful, and I can see that as like a shorter term thing. But then eventually, like, quantum encryption is going to be a really big game changer, because that's like the only like absolutely secure method in what's called a post-quantum world, where basically once we have access to quantum computing at scale, then people are going to be able to run things like Shor's algorithm. So the historic encryption methods will not work as well, but then the new methods like quantum encryption should be absolutely guaranteed to prevent eavesdropping, or at least be detectable when eavesdropping does happen right away.
Gotcha. That's great. It sounds like it's kind of limitless and exciting. I don't know that people think of engineering all the time as being exciting, but it really is.
Yes. Well, I'm excited about it. And my goal of working with students in part is to convey technical knowledge, yes, but also develop professional skills and give them excitement and motivation so that they're going to not just be able to do it, but they want to do it, and they love doing this, so that this will be their career and their identity.
Excellent. Well, thanks so much for joining me today, Peter. It was a really good conversation.
Thank you very much.
And
Appreciate your time.
Yep, and thank you for listening as we explored the cutting-edge world of microelectronics with Dr. Peter Bermel from the Purdue University Elmore Family School of Electrical and Computer Engineering. And next month, we'll have another fascinating guest and another fascinating topic. So if you enjoy these conversations, please make sure to subscribe and leave a review. You can join us next month for another discussion with experts who are shaping the future of technology.